Okay, so good morning, everyone. Thank you for coming. My name is Eric Valency from the University of Versailles, and I will present our performance analysis and optimization framework, MAQAO, along with Emmanuel Ozray at the back for the demo. So the first question we may ask is, why do we actually need a tool to optimize the code? Why couldn't we just look at the source code and say, hey, look, I see the issue is there. So as an example, where will be the issue here? This is an actual code, actually, that we had to work on some time ago. That profiling showed represented 10% of all time, and we could say, okay, where are the issues? So with some knowledge of code, we could say, okay, yeah, I know here are a few issues we can identify. We have a variable number of iterations that can prevent the compiler from properly vectorizing the code. We don't access arrays sequentially. We have very expensive instructions, square root and divide, and so on. But which will be the costliest, which will be the most beneficial to address first? We have no idea just by looking at the code. So that's why we need tools to be able to pinpoint that. Of course, we want to know, for instance, whether the issue lies in the algorithm. Did we choose the right algorithm for the job? How did we implement the algorithm? We may have completely failed at correctly implementing it, whether parallelization was correctly implemented, whether even compilation was correctly performed, because compiler flags can impact a lot on the performance of the final code, and making sure, of course, we are using the machine on which we are running at the fullest extent of its capabilities, because machines are constantly evolving now. We have passed the blessed times when machines were just increasing in speed every generation in the times of Moore's law, and we just needed to recompile our code on the new machine, and it works with the increased performance. Now we have the new feature, vectorization, specific instruction, and so on. So we have to make sure we are correctly using them, and that, for instance, you may have a code that's perfectly optimized for a given generation of systems, but when you switch to the next, it's not as optimized as it could be. Of course, what can we do to address that? We can change the source code, of course, but sometimes it just requires changing a few compilation flags to be able to obtain a speed up, and of course, making sure that various code techniques to make sure we allow the compiler to properly vectorize, to properly use memory and then the cache and so on. Another issue is being able to identify which issues we want to address first, because sometimes it can be counterintuitive when we say, okay, look, I detect that I'm spending 40% of my time there in this area of code, so I will work on that one. But if we can somehow predict that there is only 10% to gain on this region of code, it may be much more beneficial to start with a smaller section, but on which we can predict increased performance, increased gain. So the idea behind MAQAO is trying to provide insight on what the developer can actually do. So essentially changing the way the code is written, changing how data is accessed and organized. And sometimes it's just a matter of just changing some flags in compilation or in the runtime, just making sure, for instance, that you are correctly launching the MPI processes together so that, for instance, the threads are not jumping from one core to the other. So we are trying to focus on that and provide hints on what to actually do instead of just returning a bunch of metrics. Another idea behind MAQAO is that we are trying, as we say, to what we analyze is what we run. So we are analyzing at the binary level. We analyze the binary code directly. Go to heck, I know I have a VI-HPS conference now. And yeah, so we are working at binary level, which allows us not only to see exactly what the compiler did or failed to do, but also to be more relatively agnostic with regard to the source language. So as long as it's a compiled language, whether it is Fortran or C or what have you, we can analyze it and provide some information on that. So MAQAO has been in development at University of Versailles since 24. For those of you who like ancient history, its first target was actually the Itanium processor. So the idea is that MAQAO focuses much more on the performance at the core level. So compared to other tools that you will see during these workshops, we can provide information on what happens at the parallel level. But for instance, the real gain of MAQAO is to say, okay, are you correctly using your processor at the full extent of its capacities? Are you using the nodes at the full extent of its capacity? And whether do you have some parallelization issues that may warrant investigation with another tool, for instance. And also, as I was saying earlier, we're trying to guide the user. So not only provide statistics, but also hints on what to do actually and where are the issues, and try to provide also an estimation of the gain that some transformation could yield. So now MAQAO works on x86 and ARM systems. We have an ongoing work on GPU. We have a prototype that's working for profiling AMD GPUs and analyzing AMD GPU codes. And yeah, so it was a choice. We released MAQAO as a static executable. So the idea is that you can download it directly from our website, and it works right out of the box as long as you've got a Linux 64 system. And no compilation is necessary. So here are a few examples of code that we successfully improved thanks to MAQAO and our expertise. So the idea here is just to see the kind of issues that we can detect and that we can help to address. So for instance, here, this case, we had simply a function that was invoked inside the body of a loop. And it turned out that the function had always the same parameter regardless of the iteration. So we just had to remove the function call from the loop. And since a function call is very costly, very expensive in terms of performance, it yielded a very significant speed up. So sometimes it's just detecting that. For that one, we identified there was some access, indirect accesses to the in Fortran that made an unnecessary level of indirection to access structures. So we could identify that and say, okay, just instead of having two levels of indirection, you can directly access your data. We can see my pointer. Sorry, I'm gonna fix that. Let me see, laser, please. Yeah. Okay. So for this case, sometimes you can simply ask the compiler to say, okay, what did you do? And the compiler said, okay, I did not vectorize this loop because I don't think it's possible. And our analysis showed that, yes, it was actually possible because compilers tend to be conservative to avoid creating errors. So we forced it with simply adding some additional directive. And the compiler vectorized, there was no errors, and we obtained another speedup. This one was identified. So I mentioned earlier that division are very expensive operations. And so in that case, it was simply replacing it with multiplying by the reciprocal. So it's just making once the division and then multiple time multiplication by the reciprocal. And that allowed to get rid of this cost of the division. And another case also, where there were some loops that had a very small numbers of iterations. So in that case, it's much less expensive to simply fully unroll the loop and start navigating, because for very small loops, the very small number of iteration, you will spend more time checking whether you have to stay or leave the loop than actually doing the work of the loop. So MAQAO is also part of POP and has been part of many other European projects and has been integrated in some other tools. We're a rather small team. There were multiple PhDs working on MAQAO, and were various former members who have since gone to different organizations. Any information is available on our website. You can find the latest binary release that we performed. Okay, sorry, because I know I have a VI-HPS now. Okay, thanks. So we have the latest binary release that dates back to last week, actually. So it's fresh out of the box, and the one that was installed on Mare Nostrum. You can also have the documentation, various tutorials on MAQAO, the reference sheet that we'll share with you in a D3 format later on, and various also publications if you want to see the various papers and thesis reports that were done around MAQAO. We also have this. So As we'll see later, MAQAO generates reports in static HTML format. And so we have this repository setup where we share reports generated by MAQAO over various source free code that we analyze. So if you want to see what MAQAO reports look like, we have a very good database there. Caveat, some of these reports were generated by previous versions of MAQAO. So you may see for older reports, they don't look quite like the version we have now because we didn't have the time to refresh all of them. So just before going on, some very brief reminder. So this may be familiar to all of you, actually, I don't know. Just because since we are dealing a lot with what happens at the processor level, two important points. Vectorization, we'll talk about that a lot. It's simply the matter of with the cost of one instruction, is instead of dealing with elements one at a time, we can process 2, 4, 8 of them at the same time. So it's a very, very powerful tool to optimize your application. You want to make sure that if it's possible, the compiler has correctly vectorized that. So you will see a lot of vectorization mentions in our analysis. Also making sure that we correctly use the cache. So the idea is that when we access memory, it's loaded in the cache, but we load also all contiguous data in the same page of cache. So if you are jumping inside an array, for instance, cache will be completely useless because what you are loading in cache will not be used on the next iteration and will have to be flushed out by what it replaces. And also in the latest systems have these FMA that float multiplying and add instructions that basically allow to perform addition or subtraction and multiplication in one go, one single operation. So it's also another very powerful opportunity to optimize your code. So sometimes we have also reports on that to say, okay, you have FMAs, but the compiler, the processor is not using the FMA instructions. So maybe you can reorganize that to help the compiler generate such a code. So how does MAQAO work? We have this, since we work at binary level, we need to reconstruct the internal structure of the code based on the binary code. Essentially, it's some kind of low-level decompiler, basically. So we can generate, rebuild an internal representation with identifying loops and functions. One important point, you will see that in our reports, we identify loops by an beginning identifier, because sometimes a single loop in source code can correspond to multiple loops in binary code. So for instance, whether the compiler does some versioning or some vectorization with a peel loop and a tail loop at the beginning and the end to load and unload the vectors. So for this reason, we just assign an identifier to loops, and we can also tie them to the original source code. So you can see, for instance, that we'll have multiple loops corresponding to the same source location. Next, we have this profiler that relies on sampling to offer a good overall, we have a very decent precision, very good precision for very low overhead. So it's a good trade-off that allows to provide information at the function and even at the loop level. Next, we have a static analyzer. So that one does not need to actually execute the code. It will just compare the binary code to using a machine model to see, okay, we're using these instructions, they are expensive. These instructions are not the best one for this architecture. And we provide a report that says, okay, this loop is not as optimized as it should be. And maybe if you could optimize it that way, you could gain X. And finally, we have this super module that's one view. It's mainly the one you will be using, because historically we had various modules that we launched in sequence to build a representation. Now we have decided to have one module in charge of that. So it will be running the various modules and generating these HTML reports that I was telling you about. We can also generate the reports in text format, in XLS format. We'll see that just in a few minutes in the demo. So LPROF, so it's sampling based. So the idea is that we don't need to recompile the code in any way. One way that will force you to recompile the code is actually we need debug information. We don't need them to work. We just need them to be able to tie the binary code to the source code. So LPROF can perfectly work on a code that does not include the debug information. it simply will say, okay, you are spending a lot of time in the loop that address binary address 0x4x0a123. So that may not be entirely useful. So that's the one reason you could have to recompile your code. Normally, it's also required by for instance, the debugger will require to use -G if you to include debug information in your code. And also since also since we are trying to be completely agnostic with regard to parallel runtime, so we don't have very specific information about that, but we can correctly assess what's going on in the parallel runtime anyway, and just give hints to say, okay, maybe you want to investigate further with a different tool if we detect that something is very wrong with the parallelization. CQA is the static analyzer I was talking about. So we don't need to execute the code. We also need to have the debug information that's a constant, just to be able to tie what we observe with the source code. We can also, since it's static, you could also say, okay, look, analyze this loop if it was being executed on a different system. So you can just analyze on your laptop and loop and say, okay, analyze that, but consider that we're running on the latest processor on Mare Nostrum, for instance. And CQA tries to provide also hints. So just explaining in plain English, okay, maybe you want to do that because your loop is not vectorized and you want to use this compiler flag or maybe perform this source transformation and the like. I won't go over in detail over that because we'll have that during the hands-on and one specific hands-on about that in a few minutes. So CQA provides also some information in the form of what we call what-if scenarios. So we say, okay, what would happen to our performance if a given optimization was applied to this loop? And of course, if we can say, we can also predict what would happen if we manage to optimize, for instance, all loop or percent of them. Since we have the time we spent in this loop, thanks to our profiling, we can estimate the overall impact at the application level. So we have, good morning, these different scenarios. What happens if we have no address computation, essentially? So what would happen if inside the loop we are not spending any time computing addresses to essentially resolve indirections? What happens if we manage to vectorize all floating point operation in the loop, or what happens if we manage to vectorize everything in the loop? So the idea behind these predictions is that they are optimistic because we were making a certain number of assumptions. And the idea, normally if we say there is nothing to gain here, it means there is really not much to gain actually by working on that first. So if we say you have no speed up to hope by vectorizing the loop, it means it's probably already completely vectorized or that it simply can't be vectorized at all. And just coming back to the original example, this in green, you can see all the issues that CQA could detect, and not only detect, but compare to say, okay, that one may be dominant, that one will yield the most interesting speed up. So we can detect, for instance, the different strata accesses, the expensive operations, and also we can identify something that we can't see just by looking at the source code, whether we are using vectorized instructions or not. And the last module, one view. So the idea is that you don't need to bother launching L4 CQA in sequence and the like. You just tell, okay, one view, you will have to tell one view how to launch the application, which level of analysis do you want, and it will take charge of invoking the various modules and generate these reports, and try to also provide. So the idea is just one view will not be simply launching the tool. Let's say the tool said that, this tool said that. We are trying to aggregate the results together to have an additional level of analysis. For instance, just as I was saying earlier, we can say, look, CQA predicts this speed up on that loop if we manage to fully vectorize it. We see that this loop, thanks to the profiler, we know that this loop represents 20% of the total execution time. So we could have this speed up at the application level if we manage to vectorize the full loop. This is a very small example of the type of aggregation that we do. And we also try to generate higher level summaries that will say, okay, this application will be more or less tough to optimize. There are issues there, there are issues there. There are issues in parallelism, there are issues in thread activity, there are issues in vectorization, and etc. So one view can be run in different modes. The standard one is just, which we call one view one. It's just launching once the application, the static analyzer, and providing a report. We have also the scalability mode that allows to essentially run the application with varying parallel configuration. So the most obvious case will be to say, hey, I want to launch my application with 1 thread, 2 threads, 4 threads, 8 threads, etc., and just see how your application fares as you increase the number of threads. The idea is that not only you can give this information at application level, but also see which functions or which loops scale more or less correctly. Comparison mode is basically an extended version of the scalability mode. You just say, okay, I want to launch my application with different data sets, different parameters, different what have you. And we can also do actually a comparison between two completely different one view reports, or hopefully on the main application. But for instance, you could say, okay, look, I launched my application compiled with this compiler. I launched the application with that compiler. Just present the two reports side to side to see, for instance, which compiler is best for which loops. And we can also do that, for instance, for different architecture. You could say, I want to run on x86, on Intel, AMD, ARM, and just compare the results side by side. The stability mode is a very basic mode, but it should be, in my view, it should be the very first step in any performance analysis process. It simply run the application 30 times by default and just sees, observes how the execution time of the application varies. The idea is to see, okay, look, the application tends to have 5% variation of its execution time. If at some point you say, hey, look, I got a 3% speed up, then maybe you want to recheck that numbers a lot because you are just in the margin of error of the application execution time. And for instance, we had the case as part of an analysis we did as part of the POP project where the application was actually completely varying its time. And it was inherent to the application. It was a Monte Carlo analysis, so it was actually completely random. So we saw huge variations in the application execution time. So that's one when we say, okay, look, we'll have to check a lot whether an optimization is actually valid or not. So next we'll soon switch to the hands-on. The idea is that to launch an application, we'll have to provide one view with all the parameters needed for launching it. So the command line parameters, name of the application, parallel information, which runtime are you using, etc. Or you can put everything inside the configuration file that is in JSON format, and where you can just store all the parameters you want. And of course, there is an online help available. So this is it for this formal presentation. The slides are available on the website. So next, you have a further set of slides that explains what you can find in a one view report. I won't present that here because I will just show it actually. But if later on you want to come back to that, you can just look at the slides or look at the documentation. So I will now switch to a live demo on OneView. So the idea is that I will first be using MAQAO to profile a simple benchmark, a bit NAS benchmark, actually NAS parallel benchmark. So most of you must probably already be aware of that. And in the second part, Emmanuel will show you how to actually use the information in a MAQAO report to optimize an application. So I have to switch. So any questions while I guess yesterday everybody could connect without issue with the various accounts you had. So we are providing in some suggestion on which directory you want to work in. That's up to you. That's we just decide to work there. You don't have to. If you are more comfortable in working in a different directory, you can do that. That's not necessarily what's important is what's in there. these two lines were to retrieve the tarball for the MAQAO hands-on, and that's the code for the benchmark we'll use for this this demo. Additionally, on this directory, you're probably getting well that, but that's where we are storing the materials for all the presentations and that we'll have during the workshop. And that's also where the slides will be available in addition to the VI-HPS website, if you at some point require them. So where am I? Yeah. Okay. So this hands-on file essentially contains, it's a bit long to decompile, but yeah, okay. So this contains the codes for some hands-on that we'll see, and some configuration files that we'll use for profiling the application. And I don't know, okay, so it's long. Okay. So I don't think we did the exercise yesterday of compiling an application and launching it, right? I don't remember. I don't think we did that.
Well, everybody was working on their codes.
Sure. Okay. No problem. Okay. So it's a bit longer. Okay. So here we added the code of this benchmark. So I guess most of you are aware of this benchmark. This is from the NAS parallel benchmark. That's a very common set of benchmark by NASA. We have to stop that Windows. Oh. Access is slow. Okay. Okay, so the idea is that here, just to show that, we just added this -G flag for having the debug information. That is another additional flag that simplifies some of analysis. It's mainly if you're interested in retrieving information on the call stacks of the functions. So I don't know. So these benchmarks, if you are not aware of them, they're quite useful because they come in different sizes and you can just choose how large they will be. So there are a set of letters, these class letters, A, B, C, D, and F. That makes a more or less large problem. So that's that one, I think. So we already prepared a job script for just it with normally everything should be set up. If you have your own preferential, so just launching it, just checking if it's correctly. Don't hesitate to tell me if I'm going too fast. For now, this is something rather standard because I'm just launching an application on the cluster. So yeah, it should be running correctly. So normally it takes about a minute to complete. Maybe it can be a bit longer, a bit slower. Okay, so while this example is working, we'll just start looking into one view configuration file. So we already have a configuration file that has been prepared. So it's in the hands-on directory at the MAQAO hands-on BT, and we have a config BT1 view as badge.json. The idea, as I said, you can always pass parameters directly on the command line to one view. It's just easier when you have a lot of them to add them in a JSON this configuration. Just let me check where my run is. Yeah, it should probably be completed soon. Okay, so in the meantime, just let's look at one thing inside a one view configuration script. So for various reasons, we decided to use the JSON format. The JSON format is great for a lot of things, but it doesn't allow comments. and we like to have commands in our configuration file. So we emulated that by having any line with where the key is a dash. It's considered as a command. Also, if there is one option that we want to disable, we just add this underscore in front of it. So when you want to use a new option, make sure you did not forget to remove the underscore that's in front of the option. So just what's inside, we have to provide, of course, the name of the executable. Here, if you want to analyze additional libraries, that's where you can specify it in this array. By default, it's disabled. But if, for instance, your code is entirely contained in dynamic libraries, or if it's in Python, for instance, you will want to provide the names of our libraries here. We don't do it by default because you don't want to be analyzing, for instance, libmpi or libc, because it's, unless you are a libc developer, but I'm not quite sure the libc developers are using MAQAO. I would like to, but. So here you have the command line where you can specify the command line parameters that you want to give to your application. So the NAS benchmarks are great because it never requires anything. But if you had to provide some command here, you will do it there. And as you can see here, we have the keyword that's enclosed in brackets. It means that we'll be using the values that were specified up here. Yeah. So it works for a lot of stuff. You can see that in various options. So here we have all the various parallel parameters, number of nodes, process per node that can be specified here. The MPI command to execute. And one important point that you will come back later, since this time we are not launching the application directly, we are using a job script. So there is a specific system where we'll have to edit the job script actually, and I will show that in the next step. And that is where you specify how to launch the job script and what is the name of the job script to launch. Okay, I guess the job must be ended now. Yeah, it's completed, so everything is correct. So once again, if you don't know the NAS, they're quite useful because they tell you what they did at the end. They tell you, okay, look, I was running on 224 threads, and they display the time spent again. That's very. Okay, so now the next step. We will need to edit the. So by the way, I'm here. I'm using the pre-filled configuration file. You can use one view to generate a blank file that will be identical to that one, but without the preset values. I will show later on how to do that. Just here now, we just have to retrieve the job script. So just to show, essentially, we will change. I will compare with the original one. The idea is that we just replaced, for instance, any values that appeared in the original job script with a reference to the values that we specified in the configuration file. So the idea is that when one view runs, it will say, okay, I will replace that here and the like. It's useful if, for instance, you want to perform scalability run, for instance, you will not need to edit after that your job script in any way. You can just change in the configuration file the number of nodes and the number of threads and the like. Okay, next we'll launch MAQAO. So did I already load MAQAO? No, yes. So MAQAO has been installed on Mare Nostrum. So actually it's version -2600-B because we had a last minute patch. Normally, if you just say load MAQAO, it works. Yeah, you just have to launch that. You can check it's correctly loaded. If at some point I was saying you can auto generate, so one view -head. You have the online help. Oh, by the way, Emmanuel, could you please distribute the quick reference sheet? So here is a recap of all the options of one view. You can also generate which is this called that? So, create config. You can say, for instance, if you want to say create config, it will generate you a blank file, exactly like the one I showed, but without the values presets. So, and now we launch. So what's in on the MAQAO command line? You create level reports. So that's the different reports level I did talk about earlier. That this with pop flags allows to generate some of the pop metrics that will be integrated into the report. You specify the configuration file. So this is for the experiment directory. It's not mandatory to use that because, for instance, if you don't specify an experiment directory, MAQAO will generate one with a timestamp name. Yeah, it's also better if I don't forget specify which. So now one view is running and it tells you what it's been doing. So now we're just running the profiler and actually it's submitted the job. Yeah, about experiment directories, if you don't specify one view will generate one. One thing to remember when one view is able to reuse an existing experiment directory. So if you specify, so if I were, for instance, to relaunch the command by using the same experiment directory, it will try to retrieve what's inside the directory. Just to say that, because at some point, if for some reason you have an experiment that fails because one parameter was incorrectly configured, and you relaunch the same command line with the same experiment directory, when you will try to reuse it, and it may say, okay, look, there is an error, I can do that. So just make sure you use either a different directory or remove the previous one and the like. So, yeah, just while it's running, I'm going to prepare. So OneView generates HTML reports. So either you can download them locally, or you can just, what I like to do, it was actually advised by me a long time ago by Mare Nostrum administrator when we had a VI-HPS here in 2019. You can use the SSHFS, so by default it's not installed on Linux, but you can it allows you to mount remotely a directory. So, oh, it's already completed. So OneView provides the steps. So here the profiler did its job. It was generated, and now it's performing the static analysis. So it said everything, and now generating the HTML report. Oh, I did a mistake in the experiment name. Yuck. Okay. Writing that. So inside the experiment directory, there are plenty of files that are used by OneView. What's in only interested in what's in the results, where you will have the HTML files. So if you want, for instance, to look them on your system, you just need to for instance, compress that directory and download it locally, or you can use SSHFS. Just one second. So some systems also allow to launch a browser remotely. Oh, just before I start, I will launch another longer experiment. So it will take some time, and while it runs, I will be showing a OneView report. So just, I will launch OneView in scalability mode. So the idea is that I will just reuse the same command, only this time I'm using a different directory. And I just add the -- with scalability. Strong is not. So the idea is that just first looking at in the configuration file, we add this array. Why is it slow like that? So there is an array in the configuration file that specifies various values to tweak from one scalability run to the other, and it must be somewhere here. This multi-run param tabs specify various parameters that you want to change from one run to the other. So it was not used because we didn't use the scalability flag, but if you use that, it will do one additional run per configuration specified here. And it will take a bit longer because there will now be 3 runs done. So while it does that, scal, yeah, go to work. And in the meantime, we'll look inside one view report. So let me know if I'm going too fast, by the way, or if you have any question, don't hesitate to stop me. Oh, shoot, stupid me. Yeah, of course. Yeah, my Linux is allergic to Zoom, so I have to use Windows. That's fine. So just look inside a one view report. Okay. Don't know how I can move that. So I'm trying to move the. Yeah, go there. Perfect. Okay, so what you have here on this first page presents, so first here, this tab global metrics present a certain number of metrics on the application that was run. The executed time, for instance. First thing first, whenever you have these question marks, you have some information on the tab of the corresponding tab. You can hover on any line. There is this tooltip that will appear to display additional information of the metric that presented here. And when there is this little blue bar that appears on the side, I don't know if you can see it on the screen. It means if you click it, you have an additional graph to display on the right side panel. So the various metrics we have here, we have the total time. We also compute the activity ratio, that is the time during which the threads are actually active. And here you can see them over the execution of the application. So this gray line here is the total number of live threads, how many threads you actually launch. And the bars are the activity of the threads themselves. So you can see, for instance, if some threads are sleeping, for instance, you will see that the bars are much lower compared to the total number. So here you can see, for instance, the system must have been starting, so the number of threads have been launched, and they are launched one at a time, and then everybody is active, everybody is working well. If you see here threads that are not working at some points, it means probably there are some issues, either because threads are waiting for one another, or because there is an interrupt of some kind, I/O access or something like that, for instance. Here, so we tend to focus a lot on loops because that's where usually you can have the most time is spent in loops. So we compute the time spent in loops and enormous loops. So that's the most internal loops inside loop nest. We also provide some categorization of the time spent. So we say, okay, you spend, for instance, here 70% of the time in the binary itself. If you were to analyze additional libraries, it can also appear here. And we are spending 28% of time in in OpenMP, I guess. Pretty sure it's OpenMP, yeah. Just so you can see, for instance, whether you are spending time in libraries, in memory functions, string functions. We are trying to identify a few standard categories.
OpenMP means OpenMP runtime?
Yes, the OpenMP runtime. So it means we're actually, so probably there is an active barrier, for instance. That's what we see. If it's a passive barrier, we won't see it, but it will appear, for instance, in the activity threads. We will see in each shadows, actually, we will be able to see. But yeah, when see OpenMP runtime, it's really time spent actually in the runtime itself. We can see that, for instance, in the function time. Yeah, you can just jump here, but this tab functions just show the results of the profiling. So we're spending a lot of time waiting. So probably there are some threads waiting for one another. Just going back to the main global tab. So here we have the various potential speedup computed from the thanks to the static analyzer CQA that we project, or some not by CQA, not all of them by CQA, by the way, and we project them at the application level. So the various here were the various what-if scenarios for CQA, saying, okay, what happens if you manage to vectorize, for instance, all loops? We could have this speed up at the application level. So the higher the potential speed up, the redder the cell is, because it means it's bad. If you have just one speed up, it means there is nothing to improve. So it's green. You say, okay, you don't have much to gain in that regard. And here we are just trying to compute what would happen if you had no branches inside loops. So because branches inside loops are bad, they prevent the compiler from vectorizing. So here it's perfect because all loops have just one path, except very, very few that don't represent a lot of coverage. And here an estimation if we were to not spend any time in the parallel runtime, for instance, or if everything was correctly distributed. If we click here, for instance, on this what if speed up, you can hear each dot is a loop, and it's presented the potential speed up is presented with a decreasing order. So, for instance, if we just had to optimize that loop, we would have a 5% speed up, and that one next will be a 1% cumulative speed up. If we double click or click once, I don't know, on one of the dots, we open a specific detailed report on that loop. So here we see the source code of the loop, and here is the CQA report that's written in plain English. So when we try to say, okay, look, the loop is not completely vectorized, we are not using the full length of the vectors, and try to provide some hints. So maybe use different compilation flags, maybe reorder the accesses, and the like. And we have different also, for instance, advice on using an additional flag. I won't go in detail over that one because that's the topic of the next hands-on by Emmanuel. But anyway, here are a lot of hints explaining what happens in the application and how we can maybe change it either with compilation flag, code restructuring, data restructuring, and the like. And for instance, we saw here there are a lot of very expensive instructions, and we provide the line at which we saw them. And for those who want to know what's under CQA's hood, you can look at the expert tab. Those are the raw metric, not written in English in any way, that correspond to essentially the machine model of CQA. So you want to read assembly code and understand what's happened, what's behind, you can look at this tab. Now, just coming back here to the global tab, here you have a summary of the experiment, so characteristic of the machine on which you run, various the compilation option you have, which type of processor we are dealing with, and a summary of the configuration that was used. This next tab, the stop me if I'm going too fast. The summary tab is trying to prevent a high-level summary of the analysis. So first, did we correctly perform the run? For instance, we want to check, since we are using a sampling profiler, we will need that the application lasts long enough. And if it's too short, we'll display a warning here to say, okay, you are running an application, it lasted 2 seconds. We have not statistically significant results. Rerun it. So here we are complaining because we are not catching compilation information. I think it happens because we are spending a lot of time in OpenMP, which does not have obviously debug information. So this is essentially a warning to tell you forgot to compile with -g, and we can provide information, but you won't be able to tie it to the source code, for instance. So the idea is that in this first tab, if something is red, it means this code is really not correctly optimized, or the application was not launched correctly, for instance. Relaunch it. That one tries to assess some potential issues at the application level. And of course, as you can see, when everything is green, the tab is not open by default. So here everything is good. We have a good thread activity. You are spending 97% of thread are active. Otherwise, you could say, okay, look, there is an issue with thread activity. Or we could detect affinity issues. If there are some, you can identify where they are, whether you are using some additional libraries. And here we are trying to provide this type of report at the loop level. For each of the 10 hottest loops, there is a summary that actually ties back to the detailed summary I just showed, but this is a much more condensed version saying, okay, we identify these issues. Here is a penalty score that we try to estimate the level of difficulty that we will encounter if you want to address this issue. So the higher, the most difficult it will be. It's cumulative. So for instance, here we have a lot of, here for instance, yeah, there are a lot of accesses that are not sequential, where they are not unit-thread. So they add up to say it will be maybe complicated to fix. So once again, if you double click here, it will open the detailed report I just showed earlier. And stop bothering me, please. I have the zoom overlay that. Okay, here are some, here you have some detailed metric at the application level. So here we have, once again, the categorization. Only this time you can have the details for each thread of the application. So that's a good way to see, for instance, here, I guess this must be the MPL master thread or something. Yeah, there is one where I spend a bit more time. Here you can have the time spent for the 10 hottest functions across all the threads. So you can see if there is, for instance, some threads which have a significant different profile than the others. Here are some of the pop metrics that we can compute with MAQAO at this level. So they were presented to you by Martha yesterday. We'll see a bit more of them in this scalability run, actually. I just didn't show that last one, but see, since I was asked the question, we can detect every library that was used by the application. So if you need to actually analyze one of them, you can just retrieve its path here and add it to the external libraries array in the configuration file. So this tab is something you are probably familiar with if you already used Profiler. It just displays the time spent in the various functions in the application. When there is this lighter triangle here, it means the function contains loops that were analyzed. So if, for instance, you are spending time in a function that's in a library by default, you won't see the loop there. You have to specify, analyze this library in addition, and then you will see the loops inside the library. Once again, this is to avoid analyzing the libc, for instance, whenever you launch MAQAO. You don't want that normally. And here you have the details for each loop. Though once again, if you double click here on the loop, you can open the external the detail report. That tab just displays the same thing, but for the loops. So here we can see the hottest loops of the application, and you have the vectorization, how well they were vectorized, and whether we are using the full length of the available vectors. Because there is a difference. You can see, okay, you were using every access was correctly vectorized, but we are not using the vectors at their full length. Because, for instance, now we have for Sapphire Rapids, we have 512 bits vectors, but it may be that we are only using 50% of them. I don't know if we have the handy. No, one of the graphs normally displays what happens that we are not using the lengths, but we will see that in a way in Emmanuel end zone. Remove, please, the overlay. Okay. Okay, I don't go in details over that, but there are also plenty of additional. You can check boxes here to display additional columns, and you can also, for instance, here the pop metrics at loop level, for instance, for these ones. Finally, in this tab, you can see the topology of the application. So we run the application on 2 nodes. What happens for each of the threads? We can double click here on one thread to display the profile for the thread. And also you can see the actual topology. So that one may take now. Okay, great. So you can see where each thread actually run. And if you hover here, you can see lighting on the left in blue. You can see over which processing cores the thread actually runs. So that's a good way to see whether a thread is whether you pinned or not your thread, essentially. And because that is very beautiful, very nice view, but you can also have it in text format. That's a bit easier to detect. So for each processing unit, how many threads run on that one, and with the associated percentage of time, and the converse view, that's for each thread over which processing unit it was running. So I think that in the meantime, my experiment, so the scalability experiment has completed. So you can see this time it ran 3 different experiments. And I just briefly show how it looks like. Essentially, you will find the same, you will find the same thing, only this time you have the 3 runs side by side. Okay, so here you have the same type of panels, same information, only for each time you have the three runs side by side. You have this additional metric here that represents how well we are scaling compared to a perfect model. And the application will show also more of the pop metrics here. You can have all the scalability pop metrics in addition to that. Also, the function tab can also provide information for each of the run. And you can also have, you will have also, where is it? You can see how each function actually, whether it scales correctly or not, compared to theory. Let me share, So you have the parallel efficiency for each function, and you have the same information for the loops. Apart from that, it's the same things, except you have 3, and of course I showed 3 different. You can use 4, 5, 6, and you can also do that whether you are for non-scalability experiments, but you can just change the flags, the parameters, and the like. So that is it for the overview of the OneView, how to launch OneView, how to read its reports. And now we'll switch to Emmanuel. We'll actually present how to actually use the information from a MAQAO report to optimize an application. So are there any questions while we are switching laptops? And
so to start with, in a naive version, and we will see what MAQAO can do to help optimize that. So first, we will allocate an interactive session, just using 1 socket for on the node. We don't need a whole BSC node for that, since it's just a single thread program.
What's the name of the reservation? Correct.
So reservation is pop sweet tools. Yes,
okay.
It's a good one. Okay, so that's it. We have now 1 socket just dedicated for our matrix multiply. After that, if not already done, just load MAQAO, the MAQAO module, and the WISON GCC version. So on MN5, it's 14, which is sufficient enough for our needs. And after that, we just need to switch to the directory, to the related hands-on directory, which is the matrix multiplication stuff. And inside, I have prepared a make file, which has the different successive versions. The first one is original version. So just make matmul_orig to have the first version that a typical programmer will have at the beginning of his optimization journey. So we will first run without any tool to get a reference performance. And we will have something very slow. So here, quite close to 1 nanosecond for just one inner product iteration. So it's matrix multiply. So at some point, we have a dot product, an inner product, basically consisting in one multiplication and one addition. So here it's about 1 nanosecond for just one iteration of the inner product. So it's quite slow. And after that, we will rerun it, but with the MAQAO tool. So many stuff was already explained before, so I will not recall that.
Yeah, just one interesting point to note here, we'll be launching just MAQAO without using a configuration file because it's a very simple command line. And so we can just add so we took the original command line and just add the MAQAO one-view invocation before that and make sure there is these two dashes between the two of them. Yeah, okay, it's not happy with the
CapPerfMon, which is.
but that's okay. So you don't need to do the second one, just an alternative way of launching it, but using the configuration file. We already saw that.
So in BSC, we can ignore these warnings since Mare Nostrum is still sufficiently well configured for sampling to be correct. So even if we have no usual permissions for MAQAO, it's still okay on Mare Nostrum to get samples. Okay.
Meantime, I'm getting ready to open the file as soon as it completes.
So as usual, to visualize results, you can SCP or you can use SSHFS, but there is another way that was not presented. So depending on people, you can use the text output for MAQAO one-view experiments. So for instance, if you want to visualize the global tab, which was the first tab in the HTML version, you can use output format equals text dash dash text dash global. If you want the next tab, which was the loops tab, just replace global with loops. And if you want the CQA, so code quality analysis report for a given loop, since we previously here, you can see the loop with ID identifier 1 is clearly the one we want, 99% inside it. So you just put that 1 here, dash dash text dash CQA equals 1, and you will have the text the text report for that loop. So most of time people are using the HTML version, but if you want to quickly compare some reports after a small modification and you are already on a cluster, you cannot do SSHFS, or it's a pain to do SCP, blah blah blah. You can use the text output. So it's another possibility, another way for you. So you take the one you prefer, the most practical for you. So here we will use the HTML output for which follows, and we can see here. If we go to loops, okay, so you can see the first loop is not vectorized, it's all wed, 0% vectorization ratio. And if we double click on the loop, you can see that only out of 16 slots in the vector. So here it's about single precision numbers, 32 bits, that are 4 bytes. And in the Sapphire Rapids vector, you can have 512 bits, equivalent to 16 FP32 elements. So here in the diagram, you can see that you are using, your processor is actually using only the first slot out of the 16. So you could have a 16x speed up by fully filling our vector. But that is our starting point. After that, you have CQA is showing you a small figure explaining what is happening, the most probable reason why it is not vectorized. And here it's issue about loop permutation, about row major versus column major. So here we are in C. In C it's row major, but the access is actually like a column major, so it's not efficient. So you have a small example that is provided here by CQA with some colors to show you. And basically, the way you are accessing the data should be the same as the storage order. And here it's not the case. So each time you are accessing the next element in the array, inside the memory, in the cluster, it's far, far away. So it's very inefficient. That works, it's not a bug, but it's really inefficient. And that will prevent vectorization. So clearly what we'll be doing here is just permuting the two offending loops. And that was prepared for you in the next version of the matrix multiply, which is the second one named matmul perm. So just make matmul_perm. We will rerun that the same way as for the first version, and we will see something 4x faster about that. If I remember correctly, that was 0.67 nanoseconds per inner loop iteration, and now it's 0.13. So it's much faster. We will analyze with MAQAO the same way, just replacing orig with perm. And after that, in the global tab, we can see the improved execution time, hopefully. And compilation score. So here we have an issue that we can see. Compilation option score is only 50%. Since some compilation options are missing, so that are performance critical are missing, that are architecture specialization. MARCH equal here, it's x86-64, it's not specialized, it's generic for the architecture. That could be specialized for the native host node, which is Sapphire Rapids. And loop unrolling is not by default with GCC. With many other compilers, it's possibly by default, especially in O2 or O3, but with GCC, that is not by default, even in O3 and even in OFAST. And the other point we can see is the potential speedup by vectorization. That was previously 16, so we could go 16 times faster, and now it's still not okay. It's still 4x. We could have 4x speedup by full vectorization. Here we can see that instead of only first slot being used, we have now 4 slots out of 16 that are now used. It's better, but still we could have some 4x improvements. Okay, so for next step, we will add the compiler flags that are missing according to MAQAO, basically about architecture specialization that will gain 2 things. We will gain AVX512, that is the possibility to vectorize on 128, 256, and 512 bits. For the moment, we were using just SSE, 128 bits. And the second bonus is FMA. So FMA, fuse multiply hide, is for the cost of a multiply, A multiplied by B. For free, you have plus C. So we will do that. That was already prepared. Just make matmul perm OPT instead of make matmul perm. So OPT is for compiler optimization. If we run, we have a small speed up, not huge, just compared to 0.13, just 0.11 there. We run MAQAO to see what improved. Execution time has little improved, 9 instead of 11 seconds. Compilation option score is now full, 100%. MAQAO is happy. So we have both loop unrolling for GCC and architecture specialization. And the vector speedup, potential speedup, instead of 4x, it's now 2x. So it's still 2 times better. If we go to the loops tab, we can now see that the hottest loop, the innermost loop, is 100% vectorized, but still using only half of vector width. On this small diagram, you can see now instead of 4 slots being used, you have 8 slots out of 16 being used. So we still have potential 2x speed up by full wide vectorization. And you have small report here explaining that on some processors, like Sapphire Rapids, you should try 512 bits wide for vectorization, but quite often that will not provide speed up. That could, but it's not guaranteed. That's why by default, compilers are not generating 512 bits vectorization. We will still try that option. So it's just we're running the makefile with that new version, which is here enforcing the 512 bits vectorization thanks to the flag which is advised by MAQAO, which is -m prefer vector width equals 512. And we can see here we have no improvements. Instead of 0.11, we have 0.11.
So you're getting it faster, but yeah,
so it's not faster, it's not slower, but if we run with MAQAO, we can see the execution time is similar. It's about 9 seconds compared to 9 seconds. And the vectorization speedup is now 1.2. So it's very close to 1. So we can no more gain by vectorization since we are using now. If we go to the loops.
Yeah, I'm trying, but speaking to be slow for some reason. This is the last one. We'll be able to go on to coffee break in a few minutes.
So now we will opening the loop report. We can see the innermost loop is now 100% vectorized and using the full vector width. But which is funny, is it is now so fast, so efficient that it is no more the hottest loop. The hottest loop is now the outermost loop, which is driving that innermost loop. That's why we are not fully gaining compared to the previous version. So we have optimized something whose cost is no more dominant in execution. And normally you have presented that, Cedric, about a return on investment. Normally at the beginning of your, so I don't need to explain that further. And we have the feature of MAQAO. I don't know, it was not presented about comparison.
Yeah, I talked about it.
Okay.
So basically, I didn't show it, but this is how you can compare. Just say compare report, and you provide a certain number of existing experiment directory, and one view we just generate a report with all of them side by side, so you can see, for instance, the progression over our whole optimization process on how things progressed, how the various potential speedup decreased. And you have the same vision on the loops.
And I have finished.
And for instance, you can see how things progress for one loop. So sorry, we went a bit over time. Thank you for your attention. If you have any questions, but yeah.
Covering only NVIDIA devices for now. The work in progress that we are working now are extending the GPU efficiency metrics to cover also AMD devices, to compute also GPU computational metrics, and we are also extending the TALP pages support so that they can cover GPU metrics. Too fast. So this is a motivational slide why we need this yet another profiling tool, because there are a lot of profiling tools out there that they tell you how much time you spend in MPI, how much time you spend in each one of the calls, and this kind of thing. So the idea of our tool is that we are not getting the time that you spend in MPI, but we are offering you the efficiency metrics that are giving you much more insight on what is going on. So this is a very simple example where you have two applications. In this case, you have one of the processes has less work than the other, so this one needs to wait in an MPI call. In the other side, I have another application that has a lot of MPI calls sharing a lot of data. So if you use a usual profiling tool, they will tell you you spend a lot of time in MPI, but it's not giving you insight on which is really the problem. While TALP will tell you this application has a load imbalance problem, while this application has a communication issue. And from there, you can start to do the performance analysis or decide to run your application in a different way. So the MPI metrics that we report in TALP, the POP MPI metrics, this is the three that I was presenting yesterday. These are the POP metrics. And with TALP, for now, we are not able to differentiate between serialization and transfer. So we just can report communication efficiency. And we divide the load balance between the load balance that is happening inside the nodes and the load balance that is happening across nodes. I will explain this later. And regarding the computation scalability metrics, the issue is that, as I said yesterday, the computation scalability metrics are based on a base case. So as with TALP, we are reporting the metrics for this run. We cannot report the computational scalability metrics, but we get the counters to obtain this. This means that if you have two runs with TALP, you can compute these metrics. So that's, well, they are half blue, half gray, because you can compute them if you have more than one TALP run. From just one run and what we report in the output, you cannot tell it because it's just one run, but you can compute it later. So this is a summary of what the different metrics been. We discussed this a bit yesterday, but just to clarify the new ones. So the load balance tells you the inefficiency due to having different loads among the processes. And the load balance in is the inefficiency due to having an uneven distribution in one of the nodes, on the most loaded node. The MPI load balance out is the inefficiency due to having different loads in the different nodes. So you aggregate all the work that is doing each one of the nodes, and they do different amount of work. Communication efficiency tells us the inefficiency due to the communications not being instantaneous. The TALP GPU metrics. As I said yesterday, we also have now extended the efficiency metrics to cover GPUs. And this is, we created now two trees, the one for the host and the one for the device. And these are the kind of metrics that TALP will report. So we cover all the POP metrics plus the load balance in and load balance out. For the device, we cover the parallel efficiency from the device, but we are still working on the computation scalability. So to compute these metrics, we had to agree on some things. For example, we consider one GPU as a single resource. We don't take into account when computing the metrics for the device, the different streams, the different warps. We consider one GPU, one resource, and then we see if we are using it with these metrics, how well we are using it with the computational scalability. And we keep still that all the metrics are multiplicative. So the parents are always the product of the childs. So how do we compute the GPU metrics? So if we go back to what I said yesterday that we divide the execution of one process in two states, useful and not useful. Now, to be able to compute the GPU metrics, we need a third state. So we have, on one hand, the host, which are the P's, and the device, which are the G's. So we will compute this separately. And then for each one of them, we have three states. For the CPU or host, we have the useful time, the MPI time, the time that I'm in MPI runtime, and the time that I'm waiting for the GPU. And this waiting for the GPU means any time that I'm spending in the CUDA runtime, in the waiting for the GPU to finish the work, sending data to the GPU, anything that is related to the time I'm spending because I'm using a device from the CPU point of view. If I go to the GPU point of view or device, then I again have the useful time. The useful time is the time that I'm executing computing kernels. And then I have the data transfer time. The data transfer is when I'm sending data or waiting for data at any level. So this means GPU to GPU, GPU to CPU, CPU to GPU. Anytime that I'm waiting because I'm moving data. And then the GPU can also be idle because there's no work to do for some reason. So we have these three states. So if we go to the host metrics, now we are talking about the CPU part, the host. We compute the parallel efficiency the same way that we did yesterday. So it's the useful time divided by the total time. So how much time I'm using the device, the CPU to do useful work. The MPI parallel efficiency is computed assuming that the waiting for the GPU is useful. So and all the time that we compute MPI metrics in the GPU side of the metrics, we assume that the green thing when we are waiting for the GPU is like useful for the process. And then the device offload efficiency is the time that I'm doing useful work compared to the time that I'm doing useful work and waiting for the GPU. So this quantifies how much time the host is idle because it's using the devices. For the, as I was saying, for the host metrics, all the MPI metrics are computed the same way that I explained yesterday, but assuming the waiting for GPU is useful. For the device parallel efficiency, the device parallel efficiency is how much time I'm doing useful work in the device compared to all the time that I'm using the devices. So how much time I'm really using to compute kernels.
To the whole time, including the gray area, or just to the sum of the blues?
No. Okay. So the blues compared to the whole area.
Ah.
So how much time I'm doing useful work compared to all the time that I'm using the device. The load balance is similar to the MPI load bit balance, is how much time I'm waiting for the most loaded process, the most loaded GPU. So in this case, the load balance at the device is the inefficiency due to the different devices having different loads. The communication efficiency is a bit different because here what we are counting is how much time I'm waiting due to the data not being transferred immediately. So it's the ratio between the useful time that I'm using the maximum one compared to the time that I'm waiting for the data. So the purple divided by the orange. How much inefficiency I'm losing due to being waiting for the data. In this case, there are some cases when you can have two kernels running at the same time, one for computation and one for communication. In that case, I'm assuming the state is useful. So as long as I have a compute kernel running, I consider the state to be useful. If only a communication or data movement kernel is running, then it's when I consider it data movement state. And finally, the orchestration efficiency, that is how much time or how the inefficiency due to the device not having work to do. And this can be because there are no kernels left, because there are dependencies between them, because for some reason it's not getting enough work to fulfill all the resources that the device has. This is a summary of the metrics so that you have everything in the slides. And now I'm gonna show, because I have show you a lot of diagrams, but nothing real. So what do you really see? So this is the kind of things that we see. So this is the trace. This is a synthetic benchmark where we have two processes, one GPU each one. Here, blue is computing, orange is waiting for the GPU. And the idea is that most of the work, this is a kind of classical GPU application where most of the work is offloaded to the GPU. So the CPU only does the initialization and then offloads all the work to the GPU. How the TALP GPU metrics would look like. You will get something like this. And we see that for the host side, we see a low parallel efficiency because in reality, the host is not being used. And the low parallel efficiency is due to the offload efficiency. So most of the time, the CPU is waiting for the device. If we look at the device, we see that we have a very good parallel efficiency and that all the metrics are quite high. You say, why do I get a low value here if this is what I wanted to do? This is just confirming that you are doing what you wanted to do. So you wanted to upload everything to the GPU and the CPU is just idle waiting for it. So if that was your intention, these metrics are telling you that you are doing that. So it's good or bad. It depends on what you wanted to achieve. If this is it, then you will get something like this. Here we have the opposite situation, an application that it's not using the devices so well. The CPU is working most of the time and just a small portion of the kernels are being offloaded to the GPU. Then the metrics that we get are very good for the host because the processes are almost all of the time busy and working. So the efficiencies are very high. And the device, on the other hand, has an issue with the orchestration efficiency because it is idle due to not having work. So that the host is not offloading work to it. So it's just idle waiting for work. So I have more examples. You will have them in the slides if you want to check, but I'm not gonna go over them because it's a bit boring. And I want to show other use cases of TALP. And then Valentin will do the demo and show you some live stuff. So the use cases, as we call it, is we can have the transparent user use for the user. So this is the very basic use case where you don't need, the user almost don't need to do anything, and you get the metrics without doing anything. Then we show the example where with user-defined regions, how you can define the API to define those regions and what you get. how you can get the metrics at runtime, and then also the TALP pages, what it is, because I have been mentioning TALP pages, but I have not said what it is, but you will see it now. So the very basic use case, the almost transparent for the user. We just define the DLB args that is telling the DLB library what it does to do, what it needs to do. So we tell them I just want the module of TALP enabled, and I preload the library. That's it, nothing else. And after your execution, you get an output in the standard output like this, where you have a summary of the efficiencies. In this case, the example is an MPI plus OpenMP application, and you see the MPI metrics, the OpenMP metrics, and the computational metrics that are the hardware counters. This is the easiest one, where the library will intercept the MPI calls, gather the information, and then at the MPI finalize, produce this summary. Now you want to go one step further. You want to instrument your code. Then you can use this API. With this API, we define different regions. Here we define the region, and then once we have the region defined with a name, we can start and stop as many times as we want, as nested as we want. So there are no restrictions. They can be nested inside, but also nested like this. You can do any kind of nesting you want. And you will get something like this. Now you get in the output the metrics, but you get different sets of metrics. You get the metrics for the main loop, because you annotated it, for the kernel computation, and the global one. The global one, you always get it, but it's from the MPI initialize to MPI finalize. So the global, you always get it, and then you define two additional regions, and you get the metrics for those regions. What happens with the kernel computation? That it doesn't have MPI calls. Then we don't have MPI parallel efficiency metrics. Okay, so depending on the region, on the details of that region, we also have some metrics, and others doesn't make sense. For the main loop, we have the parallel efficiency because there are MPI calls inside. Getting a bit more complicated, then we want to get the metrics at runtime. We are a very smart application, and during the execution, we want to know how we are performing. You could implement something as easy as saying, okay, if my parallel performance is below 60%, just abort the simulation because I'm wasting resources, for example. For this, what we can do is, when we are running the application, at some point you call the get metrics API, and with that data, you can decide to take decisions on your own. This can be done from within the application, but this also enables other resource managements there to implement optimizations. And this is how the API looks like. So you register the region, and then for that region, you can get with the monitor object, you can get the values for the different metrics. So one success story that we did using this, for example, was using Alia, one of the codes here developed at BSc. We plugged everything together, TALP, Alia, and comps. And what we did is, Alia was the code that was asking TALP for the efficiency metrics. Depending on the efficiency metrics that Alia was getting from TALP, Alia would decide to adjust the number of resources it was using to run dynamically. So what we did is this. We had a target communication efficiency. We said, okay, I want my simulation to be in this target efficiency. And then the blue line means the number of cores I'm using. The red line is the communication efficiency that Alia was reading. So these are the time steps. And what happens is, Alia is running, it's measuring the communication efficiency. And after a number of steps, it says, I'm below the target communication efficiency. So I will decrease the number of resources that I'm using. So I will run with less nodes. Again, I measure, I'm running now 40 instead of 90, probably I was here. I'm still below the target communication efficiency. So at this point, I decrease again the number of resources used. And here is, with this number of cores, with 20 cores, is when this simulation reaches the communication efficiency that I want. We have the other case. We were starting here. This is the target communication efficiency. Our communication efficiency was here. So we still have room for improvement. We ask for more resources. Now, instead of 20, I'm running with 30 cores, still above what I wanted to achieve. So I can still increase the number of resources, ask for more nodes. I'm still above, so I'm good. So I will ask for more resources. And when I'm here in this number of cores, it's when I reach the target communication efficiency and I stay here. So this is something that it will allow you to do dynamically.
Is there any particular feature of this area application that allows this dynamic balancing of reordering the resources to do well? Or
now, in this case, we were relying on checkpointing and restart. From when we did this work, they have been working on doing this more dynamically with adjusting dynamically the number of MPI processes. But one of the main issues is that's why we needed to use comms. Is that right now Slurm doesn't allow to say you're running with 100 cores and you say give me 10 more or nodes. Give me 10 more nodes. This is something that Slurm is not handling very well, and is one of the limitations to do this.
But once you find the optimal number of cores, you're good to go. I mean, that's the configuration. It doesn't change during a simulation, right?
It depends on your simulation. In this case,
once the simulation is settled, that's the optimal number. It's not going to change during runtime.
But it depends on your simulation. I mean, imagine that you have one of these, how do we call it? The refinement of the mesh, the adaptive mesh refinement.
Yeah.
And then you do one mesh refinement, then your communication maybe goes down or something.
So you don't get, you have to do this process every time, basically, for simulation.
Depending, it depends a lot on your simulation. So ideally you do it the whole time. If you know very well that your simulation is quite stable during all the time steps, then you can just do it at the beginning and then say, I'm stable, I can stop. So TALP pages, what are TALP pages that I have been mentioning? TALP pages is the idea of using TALP to integrate the performance test inside the CI/CD system. So the usual CI/CD works like, okay, I do some development, I do a commit, I run the correctness tests. If they work, I go back to development. What we say is, should we add, after the correctness test, a performance test, gather the performance that we are doing, and then we're going to start again. So the idea of this is to integrate the TALP and the TALP metrics with the CI/CD system. And we have two ways of doing this. One that is only the scaling, and you get a plot like this. This is a single point in your commits. So you have one commit and you run different tests and you see how your commit scales. In this case, for example, we see at the top that we have different configurations of MPIs and OpenMPs. So we are increasing the number of MPIs. And we see, or in this case, for example, changing also the OpenMPs. And we see how the metrics change when changing this configuration. This will be like the more classical scaling tests. but done automatically with TALP and getting all the metrics and drawing it in a table. But this is the example where we use and we measure the metrics to see the evolution with the different commits. So here we have the time, and every bullet that you see is a commit. And the different metrics, the different plots show different metrics. But if we look at the top, and the different lines correspond to the different regions that we annotated in the code. So we have here highlighted 3 regions, which is the application, the whole run, the initialization, that is the greenish thing, and the time step, that is the bluish thing. We see here that we have 2 commits, that there's almost no change between them. But between this commit and this one, we see that both the application and the initialization reduce the execution time. So we have here 1 commit that improved the performance of our code. Why this commit improved the performance of our code? We can check then the other metrics that we have below. There's no change in IPC, no change in use for instructions, no change in frequency. The change is in the parallel efficiency. So with the last commit, we improved the parallel efficiency of the initialization part of the code, and this improved the overall application. So we are just showing here the parallel efficiency, but you could also check if it's the communication efficiency or the load balance. So this is the idea of the TALP pages, so that you get it integrated in your CI/CD, and you can get this kind of plot for every commit that you do if you run the performance tests. So to finish with the boring stuff and leave you with the fun stuff that Valentin will show, TALP is a lightweight tool that allows us to gather the efficiency metrics. We can do it at finalization, just plotting all the metrics and giving you all the information. And also it allows the integration with CI/CD systems. But we allow also to get this information at runtime that allows us to adjust things at runtime. The most important thing is it's low overhead, so you can use it in your production runs. You're running a 1,000 cores, 1,000 nodes simulation, and you just want to understand if it's going well or not. You plug in TALP, and at the end, you will get the information. And you see, okay, this simulation had a very bad load imbalance. It's better to fix that before launching the next one, for example. It does not store terabytes of data because it's just profiling, so we don't have a trace. And the idea is that with TALP, you get these flags of something is going on, and then is when we need to get a trace and really do the detailed analysis. So it's something that you can run always, and that way you get these flags that something is not working as you wanted. And we also provide the API to annotate regions, which increases a lot the information that you get from that. Okay. You have here the information of the version, and also where you can download it, the user guide, the hands-on, and so on. And now Valentin will show you a bit real stuff.
All right. I will sit because I have to type. I hope everybody can understand me. Also in the back, and you can see my screen kind of. So, perfect. Okay. So, I prepared a small live demo of the most interesting capabilities of TALP that we're going to go through. I'm a nervous typer, so let's see. And GPFS is a nervous file system. You might have experienced it sometimes if you're doing LS. It needs to think for 20 seconds, like how do the files really look? So let's see if it actually works. So first, we want to start with a hybrid application that you all know from yesterday. So I compiled Vlasiator again. because it's a real application and it behaves nicely. So all the things we will do will be with Laziator. First, we will look at what information can you get by just preloading TALP without anything, without any regions inside the application. Then I put some regions, in this case only 4, into Laziator, and we can see already how useful that is for MPI plus OpenMP applications. After that, Laziator, since a few months, has a GPU version, which we can also just have a look at with the same regions inside. And then we will discuss a bit what we can do with the data that we have in terms of integrating it into CI, for example, with TALP pages, or just post-processing it normally. So let's start. The most basic use case is just loading the DLB module, exporting those DLB args. And actually what I want to show here is the documentation. So if you go to DLB docs, read the docs.io, what you can see is basically we provide you for every kind of execution that you have with an example DLB args and how to run things. So let's go into my terminal. I'm somewhere here. Please don't modify files. You can copy them out, and I will tell you later how you can copy them out if you want to try it yourself. But for now, you can just sit back and relax and watch me type. No need to follow along on your machine right now. So what do we do here? First of all, the typical Slurm stuff. For this, we request 8 nodes because why not? Laziator is in fact a bit memory hungry. So this case runs on 4 nodes stable. I couldn't get it to run on 2. I did the Laziator installation here with the typical HPC environment.sh. I list all the modules. And then I basically just load DLB. This one, hey. I of course wanted the no regions. Then I just export the DLB args to be type OpenMP because we want to also get the OpenMP metrics. OMPT is the flag that we also need for OpenMP, and type PAPI. For type PAPI, note that you need to use the SBatch constraint paranoid because otherwise PAPI will not work in Mare Nostrum. Exactly. Then what I do is basically I make it a bit more obvious for us. I hope you can read. So I just set the LD preload and preload libdlb MPI. This is just my Laziator binary, and then I run the magnetosphere input. So we can just schedule this, and let's see how fast we get a queue. Then what we can also just put into the queue is basically the same thing. So it's the same job submission script, but in this case, I export of Laziator type regions equals to 1, which is kind of a magic flag in my version of Laziator that gets read and then puts type regions in or not. So again, DLB args, we preload DLB. So let's scratch that as well. They're waiting. We don't need to wait for them because luckily, wait, where is it? Okay. Luckily, I actually have prepared the output of it. I hope you can read it. So this is the output that you would get after, I think, 3 minutes is the rough runtime, or 85 seconds actually, on 8 nodes. So we can see that DLB35 is loaded. This is the hello, I work message from DLB if you preload it. If you don't see this, you didn't preload it properly or you didn't specify any DLB args. Then this is output by Laziator, basically saying, yay, I computed the requested simulation. And then we see the pop metrics that type reports. We can see the useful IPC because we specified type PAPI. So we read actual hardware counters. We can directly see that parallel efficiency is not great. 22% on 8 nodes is, I'm scaling this case a bit to the extent, And we can already see that, for example, communication efficiency and load balance kind of have similar roles, and that most of our load balances in the nodes. This now contains the whole application, okay? With all the initialization, with all the time stepping. So for this, I did 10 time steps. If we actually put regions, let's see if we, okay, so now they're running. If we actually put regions, just for you to know what kind of regions we're talking about. So this is the slide from yesterday. I instrumented the propagate, okay? The initialization, which is all of this. This red thing is called initialization. I instrumented the green ones, which are called propagate, which are the time steps. And then in the time steps, I instrumented velocity space, propagate fields, and spatial space. So we have these kind of big regions because this is the bluish one is the spatial space. The red brownish one, this one here, is the propagate fields, and the velocity space updates are also instrumented. So I just put regions around these already there regions, and we will see them hopefully in the output. So which one was which? I think this one was the one with regions. Yes, perfect. So this one is the one with regions just finished. We can again see that execution took about 85 seconds for the global region, which is the implicit region that type always creates, which roughly reaches from MPI init to MPI finalize. With OpenMP, this can be a bit more tricky, and with CUDA applications as well, because how we initialize DUB, but roughly MPI init to MPI finalize. And we can already see that the initialization took roughly 31 seconds of this with a parallel efficiency of 20%, which is not great. And we can actually see that load balances most of the problem here. And we basically don't use a lot of OpenMP as well. So there's a lot of serial code in the initialization. If we now look to the time step, we can see that the time steps, the 10 we took in total 50 seconds with a parallel efficiency of 25%. We can see that we do a lot more OpenMP. So we have roughly half of the runtime is parallelized with OpenMP. And parallel efficiency in MPI seems to be, again, mostly bound by load balance in the nodes. Not across the nodes, but in the nodes. We can now go down to see the propagate fields, or the spatial space, or the velocity space, but you get the idea. This is basically one way to put it. Now, exactly. What we can also do is, instead of getting all of this to the standard out, because in the end you might want to post-process it or pass it somehow, is just tell type, hey, can I please get this as a file, as an output file? And here we support multiple options. Let me change back to the documentation real quick. So here we basically, in the type documentation, I hope you can read it, we basically have multiple options of how you want your data to be presented. We support CSV and JSON, where the JSON contains all the information. The CSV also contains all the information, but yeah, we deprecated XML, so please don't use it. It will be removed in a future release. So what I'm going to do now is, because why not? I basically run two scaling runs. So here I have 4 nodes Blasiator, which I just call type 4node.json. Okay, so we can do a typical scaling analysis. And then I also have an 8-node script, which just uses 8 nodes, obviously. So here we have the 8 nodes. And it produces a type output file, which is called type 8nodes JSON. Once those are finished, we can then post-process them. While those are running, we can switch over to, so cover this. to GPUs, because in the end, using CPUs is nice, but if you want to actually run on modern systems, you will at some point have to use GPUs. And actually, so for this tutorial, this is the first time I ever used Blasiator with GPUs and TALP. So I compiled Blasiator once with GPUs a few months back, but I just compiled it the other day and preloaded TALP and everything worked. So what do we have to do to make it work? This depends a bit on how your application looks. We again provide you with a lot of insight. So if you have an NVIDIA GPU execution or a hybrid MPI plus GPU and so on, there's different options. Also, we support AMD. But basically, you will need to select a plugin. So let's have a look at the job file here. This is now on the accelerated nodes in Mare Nostrum. We just grab a whole node. We want it exclusively. We want 4 GPUs. Then this is the Blasiator installation again. I load DLB. I run NVIDIA SMI to check that I see all the devices. This is a small Mare Nostrum 5 MPI thing that you need to put, otherwise it will not work. And then basically I use the same binary, yeah. So just compiled with it, not the same binary, but the same source code, just compiled with a different compiler, and with, of course, GPU enabled. So I export the Blasiator type regions, and I just tell to DLB, hey, type and use the CAPD plugin, please. Then again, something very Mare Nostrum related, where I need to make sure that the processes only sees 1 GPU. So each of the MPI processes that I spawn only sees 1 GPU and gets the correct GPU assigned. And then again, I just preload the same MPI library as before. Different input file. Now we're waiting for GPFS. And we can just launch it to later look at it. Perfect. Let's have a look at our jobs. They're still running. Probably they're trying to root files. So what we basically did is we did now a hybrid scaling test with CPUs that is currently running on 4 nodes and 8 nodes. And we just launched a GPU version of the code that we will hopefully understand a bit better how it uses the GPUs without needing to trace anything. Okay, so let's have a look at the 8-node JSON real quick, so you have an idea what the JSON looks like that we get. I just opened it. In the beginning, it just tells us the timestamp when it was run, the amount of resources it was run, and then in the applications tag, we basically see all the information. No need to understand everything, but what you probably want to look for is those efficiencies down there. The upper part is basically all the raw information that we use to compute the efficiencies, and that are available also in the DLB monitor. So all of these metrics are also available in the DLB monitor if you want to query it at runtime. And then we can basically see the different regions, initialization, propagate, and so on. But this is not very nice. These, let's wait for the other thing to finish. And someone is using the GPUs. Oh no. Luckily, I did run before with the GPUs. So while the CPU thing is running, we can have a look at the output for the GPUs. So first of all, the GPU code runs quite long. So it takes like 4 minutes, I think, 5 minutes. And we can also explain why. So initialization takes a whopping 180 seconds and has very, very, very little device use. You can see that the parallel efficiency of the device is 3%. So we're basically not using any GPUs in the initialization. still we're waiting for 40% for the GPU here. So not great. If we now look at the thing that most people are more interested in is the time stepping, because who cares about initialization, right? It's a one-time cost. Time steps are the most interesting thing. We can see that Vlasiator actually did a better job of using the device. Not great, but a better job, I would say. And we can directly see a lot of things without having to know the application. We can see that we have a little bit of a load balance communication problem, so we wait for MPI quite a lot. Load balance seems to be quite good among the 4 processes that we have, and device offload efficiency is low, so they don't do useful computation while waiting for the GPUs, basically. So one of those typical codes that tries to offload as much to the device. What we see here is that the 4 GPUs that we're using are not perfectly balanced in terms of the timings between them, with only 85% load balance. And most efficient, or most significantly, we don't give them enough work. So the orchestration efficiency basically tells you how much work do you offload into the device, how much overlap you have there, and this is a very low value. So the GPU is basically idling 28% or 1 minus 28% of the time. Yes. Yes.
So
that are basically produced right now. And what we can do is I prepared another demo in the type pages folder, where I basically copied them beforehand. So these are just the same JSONs just from this morning. And we organized them in a, let's do it like this. We don't want the Python virtual environment to show me all its insights. So what we basically did is organize the type JSONs a bit. In the end, what the idea behind type pages is that you have like an archive of JSONs you collected from runs, and your job is to organize them by folders in a subfolder. So we have one main folder, and then we, for example, let's actually rename CPU into CPU strong scaling, because this is what we're doing. So we run a strong scaling and test, and these are basically the 2 JSONs that we have. What we now can do is we can just do this. So type pages is basically a Python package. So I have to activate my virtual environment, and then I get the type binary, type command line tool, which does a lot of file accesses apparently. Okay. And here's basically the things it can do. What we now want is a CI report. So let's see how this works. Well, we can provide an input path, an output path, some regions that we want to have, if we want a batch or not. So the input path is basically the upper level folder, and the output path, let's say, is type report. I already prepared that. Now we need to use force to override the output directory if present. And we want to put regions, which let's use only propagate. What type pages will now do is basically go ahead and process our subfolders that we gave it. In this case, it's only a strong scaling experiment, but let's say you have a code that runs different mesh sizes, different input configurations, different solvers. You can basically put all of these in subfolders and keep them around. It does file accesses. So once this is finished, what we would get is basically a simple HTML page that we can just download to our machine and open with Firefox. Which will look something like this. So this is now the CPU folder because I did it this morning. 943. And basically, this is the two options that we have. So we have for every resource configuration, we call it, we have a evolution plot available that we can click, which we only have one data point, so it's quite boring. We see the different regions here. And we have, of course, the scaling table. In this case, for the propagate region and for the initialization region, where we can directly see no grade, and there are no interesting trends. Maybe interesting here is the IPC scaling, that we speed up a bit when we strong scale, which is kind of expected from scaling up because you have higher cache efficiencies and so on. Yes. So now, why is this interesting that it's actually an HTML? Well, because you can integrate all of this very nicely into your typical GitLab CI workflow. So what we have here, for example, is this is one of those batches that we create. For example, parallel efficiency 5%. What we do here is we just run some NAS parallel benchmarks, I think, yes. NASA parallel benchmark suite with TALP installed in a virtual machine that we have. It's not the biggest machine, it's not an HPC machine, and the PAPI counters are broken. So bear with me. You can see that there's a few nulls here and there because the PAPI counters are broken. It reports, it says it can do PAPI, but then it actually cannot. So what this would look like is like this. So you would see, if you hover over it, you would see the Git commits that generated this performance report. And you would see the branch and so on, the time step that it was executed, the Git commit happened, and the elapsed time. In here, we don't expect to see any performance improvement because it's just running the same benchmark again and again and again. But we also didn't expect to see any change. You can see that the useful instructions go a bit cuckoo, which is again to the fact that PAPI is kind of working sometimes in this machine. This is actually an Intel test chip, Intel engineering sample chip that we have somewhere in this house. So all bets are off with this machine, basically. But it's our CI runner. So I just occupied the CI runner that we normally do to do linting and stuff, to run these kind of things. Go back to my presentation. Let's look if the GPU thing might have finished. It did. So we can actually look at the output, and you don't have to trust me. Again, this is basically the report we get, similar to what we've seen already. Now with a bit more detail. We know that propagate fields is one of the subregions. Hey. Look, there's a small printing bug here. Ah, no, propagate fields. Propagate fields is not parallelized with GPUs, apparently, because you can see no NVIDIA device category here. So that's interesting. I didn't know this before, which makes sense because the field solver is written a bit differently. Spatial space, not very efficient. And the velocity space, which is also the most efficient on CPUs, by the way, is also using the GPU the most in terms of respective time percentages. Okay. I think so much for we did this. So much for the introduction. I want to mention that we have this quite nice documentation. If you run into problems, let me know. We can update it very quickly. But we try to keep everything in there. For example, what I didn't mention is with OpenMP, we rely on OMPT, and this depends heavily on your compiler if we actually can support this. And we made this little matrix here, depending on the compiler that you're using, if we can measure or if we cannot get the OpenMP matrix for you. Yep, that would be about it. Are there any questions?
Yeah, so we learned a lot about TALP, and now we come to from the usage point of view, a very similar tool from our side, which is called the OTF-CPT. OTF-CPT stands for On-the-Fly Critical Path Tool. And why it's called like this, I will talk about in the next few minutes. Like this, so you can actually see me. Okay. First, I think we talked about the model factors a lot so far, so I'm just going to quickly go through. Basically, we have this tree metric as well. So we compute the pop metrics just as the other tools do. And we have this tree kind of metric tree, which consists of the parallel efficiency again and some parallel efficiency that splits up into load balance and communication efficiency, but communication efficiency also splits up into transfer and serialization efficiency. And when we have hybrid OpenMP plus MPI setups, we split up the whole tree into those two subtrees. So we have the MPI parallel efficiency and the OpenMP parallel efficiency. We know that from other tools as well. We saw that in TALP, and yesterday in the introduction, we also saw that from the BSC and JSC tools. However, the important part is splitting between MPI or between serialization efficiency and transfer efficiency requires a little bit of more computation, since we need to find out what the actual possible ideal runtime would be. So our tool offers a very lightweight way of computing those two metrics, the transfer efficiency and the serialization efficiency for both MPI and OpenMP. What exactly the efficiencies mean, we'll come to a little bit later. But basically, just to remind you, we have this multiplicative tree. So every single metric that we compute is between 0 and 100. And two child metrics multiplied will result in the parent metric. So our tool does the same thing, computes those metrics. So you might ask, why are we doing another tool? And our main point is that we can differentiate between the transfer efficiency and the serialization efficiency without having to have large trace files or a large computing overhead after, or post-processing after overhead after the measurement. So what are we exactly measuring? Basically, we need three different values that we need to measure. First one is the useful computation or the useful time, which means anything outside of parallel runtimes, so anything outside MPI and anything outside OpenMP, we consider as useful, mostly as the other tools do as well. However, if you look into adding GPUs to the mix, you might as well say, okay, if we are in a CUDA runtime or something, then it's also not useful. But we are currently just focusing on CPUs. We are developing something for GPUs, which is not released yet. So we're just sticking with CPU parallel runtimes. The real runtime is just our complete runtime between start of the application and stop of the application, or start of any marker and stop of the marker, basically including everything, useful computation and parallel runtime. And finally, to split up into the transfer and serialization efficiency, we need a thing called ideal runtime. So ideal runtime means what is exactly the runtime if we don't consider any parallel overhead we get. So for example, if we send something from one process to another process via MPI, there is, and we do a synchronous send, for example, there's some time that both processes spent in the MPI runtime without any useful computation happening. And our ideal runtime would be a runtime that is ignoring that parallel overhead that we get from MPI or from OpenMP. So this ideal runtime is very hard to, or it's not very hard, but it needs some post-processing, usually from a trace file. for example, the BSC tool to do that with the MEMAS. You will get to know this, I think, tomorrow with a simulator. And Scalaska also does some trace analysis to find out this runtime, this ideal runtime. And our tool just tries to get this metric or gets this metric by some assumptions on the fly, which means during your execution without any post-processing. And our assumption is basically the execution of the ideal runtime is our useful time on the critical path of the application. So we assume 0 communication costs. Basically, our MPI runtime is completely ignored. Our OpenMP runtime is completely ignored if all of the threads or processes are in this runtime. So I talked about the critical path. You may wonder, what is the critical path of an application? Basically, the critical path of an application is the path through our parallel trace that defines our total runtime. It's the longest chain of dependent useful computations. So if we have, for example, this kind of setup where we have 2 threads for 2 processes. So in total, there's 4 threads. And we have a situation where yellow is, for example, our useful time. MPI is depicted in red here. And blue is our OpenMP time. And we get a trace like this. Of course, in our tool, you wouldn't see this trace, but you could see this trace with other tools. But it's still a good example to just show you what happens. So our critical path now is defining our total runtime, which means, okay, if we look here, there's some synchronization points where both are in MPI, but this one took longer with the useful computation. So this one is the first critical path, but now our critical path switches to the top process because the total time that basically is taking of all this useful computation that is happening here, it takes longer on this top process. So if we optimize anything on this bottom process here in the middle part, it wouldn't shrink our total runtime. Because if we optimize here, for example, so we stop this whole useful computation here and we're faster, this guy is just going to wait longer on the top process. So we need our critical path goes through the top process here. Now we split up our critical path into threads as well. So we look at in this trace, we look at which thread is doing more useful computation, which is waiting longer. This one is waiting longer in the OpenMP runtime. It might be a barrier or something. So our critical path now goes through this second thread on the first process. And then we go back into our, there's a join here between the 2 threads, some useful computation, and finishing our critical path. So our critical path defines our total runtime, and optimizing outside of the critical path doesn't immediately gain any, or doesn't gain any performance here or gain any runtime decrease, because we only need to focus on the critical path to decrease our runtime. So our tool tries to find out the length of the critical path to get this ideal runtime and to compute all the pop metrics by doing just a forward analysis. So where other tools actually compute the critical path, so for example, the JSC tool Scalaska will actually compute the critical path and know afterwards, post-mortem, after the run, what exactly were the functions that were on the critical path. We don't know these functions, but we know the length of the critical path. So what we do is, if we go back to our example, what we do is on every single synchronization point, we basically take the maximum of the useful computation of the currently involved resources. So for example, these 2 processes, this maybe has 1 second of useful computation, and this one has 3. So here we take the maximum and we know the length of the critical path, the useful computation on that is going to be 3. and we propagate that along the critical path. So now we continue, maybe these two threads, they both have a clock, a thread local clock, and they run. And now here we know this bottom thread was the longer. We take the maximum, so the length of the critical path is going to be this plus this. And of course, we do that on the bottom part as well. But here in the end, we're going to notice the top one was the longer one. So the top defines the length of the critical path. We take the maximum at the end, and this gives our length of the critical path in total. And now we can use that number to actually compute the POP metrics and split up into serialization and transfer efficiency. To get all the POP metrics, we are considering 3 different times, or actually 2 different times on the critical path. One is going to be the useful computation, which is just the yellow part in the last example. And the second one is the time outside the OpenMP runtime. So we are computing the metrics basically bottom up. We start with the lowest metrics, compute them, and then combine them to get the top level metrics again, to get the parent metrics. Also, we define several critical paths. Now I just showed you the global critical path, but you can also think about, go back to this example, that if we just have a process local critical path, we could say, okay, if the process local critical path for this top process would go through here, go here, and then go here. And for this one, it would go like this, go also to the bottom because this one is longer than this, and then go here. So we have a process local critical path and a global one. And then finally, we also have a thread local critical path, which is kind of boring, but because it just goes through the whole thread execution, but we can still compute the useful computation and the time outside the OpenMP region for each thread. That means we have these 3 values that we can use to compute our POP metrics. All right, so let's go to the actual usage. How do we use this tool and how does it look? And you will see that it's very similar to TALP. We also just run our application. So for example, if we have an application using 32 processes and 8 OpenMP threads, and we do an MPI run with the hybrid application. So we don't need to recompile it, just run it nobly, but we add some more parameters to that. So for first, the tool is provided as a shared object or shared library. So we can LD preload it. So first, as in TALP, basically we do env and then set the LD preload variable to our lib OTF-CPT.so. And then also for the OpenMP analysis to work, we need to add this OMP tool libraries flag, which basically sets in the OpenMP runtime the correct library as a tool library. So this is our whole call. And after the app output at the end, we also get these metrics, a little bit different format. And as you can see, we have the MPI parallel efficiencies and the OpenMP parallel efficiencies. And the combined metrics up to the top metric. Also, we print some statistics over about the application, so how many threads in total, and the average computation and the total runtime. And that basically concludes our output. Once we have that output, yes, you have a question? Or, oh, okay. Once we have that output, we can parse it with a script we provide. This script is just a Python script which parses all the output. And then you can have multiple runs in a directory. It uses the output of each of the runs and then combines them into 2 different visualization. First one is we get some kind of plot that shows us how basically the metrics change over our resource increase. So on the x-axis, you see our different runs. We started with a single MPI process, 2, 4, 8, 16, and 32. And on the y-axis, you have our efficiencies. And we can see the blue one. It's basically our parallel efficiency, which goes down. And then for the rest, we stack our our child metrics that make up the parallel inefficiency in total. So on these visualizations, all the other metrics that are not parallel efficiency are basically parallel inefficiency that is stacked up. So you can have a quick look at how these parallel efficiency, why the parallel efficiency is going down. And in this example, we can see the load balance for OpenMP and MPI is decreasing. That's why the inefficiencies are increasing here. So this red and orange part, which relates to load balance OpenMP and MPI, is increasing and getting larger the more resources we add. We also have two different plots for, one is MPI, just the MPI part, and just the OpenMP part. And then finally, we give you a little runtime plot so you can see how your application is scaling. The second visualization we provide is this table. This table is basically the same that you get from most of the other tools. For example, the basic analysis tools from the basic analysis script from BSCs, giving you the same table. So we have our efficiencies color-coded from green to red, whether it's 0 or 100. And then finally, we also add our computational scalability that is not part of the standard output, but is computed in our script, which is just the total amount of useful computation. If we increase our runtime, the computational scalability goes down. All right, so this is first like a little bit of slides, but let's actually show how we do this. So I have prepared a little version of the NASA parallel benchmarks, which is in the Scratch folder under exercise OTF-CPT. If you want to follow along, you can use it, or you can check it out later. Basically, it's just a complete normal version of the NASA parallel benchmarks, but I added a sleep at a certain spot to add some load imbalance artificially, just to show you something on the table in the end. Because if I just use the table without my modification, if I use the tool without my modification, the table would just show perfect metrics because the NASA parallel benchmarks perfectly scale. All right, so once we look into our code, I have pre-built it already. If I can type, that's better. We can use a couple of modules here. If you type in, I have to get the. So there is a couple of module files I installed for the critical path tool. They are all under this path, GPFS Scratch NCT 362 RWTH modules. And when I use the module folder, I can go to check our modules. I've pre-built 3 different versions. Since we are attaching to MPI and redirecting, we have to rebuild for the exact MPI run library that you will be using in your code if you want to use this tool. This one is the standard one that I'm going to use for now. So we load this OTF-CPT module. It also loads a couple of other modules that are just the ones that this one was built. So we can make sure that if you load this module and build your own code, you're on the same it hopefully just works. All right, so I've pre-built this this application already, and won't build it again. But also I provided two scripts. One is called the run.sbatch, which is our Slurm script. This one is just, actually I need to look here because for some reason the Zoom overlay is just over this thing. It's a very small run, just 5 minutes, because I shrink down the iterations because the sleep added a little bit more time than I intended. We load our module, and then as you can see here, down here, we can just use the lib OTF-CPT.so to attach our tool to the code, and then we add and run this D-class benchmark. And to get a little bit more runs, I also added this other script, which is called submit CPT jobs. Let's look at that real quick, which is just a loop for these couple of runs that I did, 1, 2, 4, 8, 16, and 32. And I use different amounts of tasks, so MPI ranks, so Slurm tasks, and also modified the output. All right, so let's run our submit script and let it run for a bit. We can wait now until they are all finished. I have this, can also use SQ. I always put my aliases in. It's just just convenience. I also have the outputs already, so let's look at the outputs. So, for example, I'll run the 32 run. So after the total run, I shrink down the iterations. That's why it says failure, but this is just the benchmark not confirming that it was correct, but it still works for the purpose of the pop metrics. And in the end, you get this output. So we took around 13 seconds in total. So it was a really short run. And only 2 seconds of, or 2.6 seconds of those 13 seconds was, was actually computation. So our parallel efficiency is really, really low at around 20%. We can see that around 50% goes to the load imbalance of MPI, but the OpenMP load imbalance is way worse. And once I have all the outputs, I can use our script, which is called CPT plotpy. I can give an output directory, which is called CPT results. And finally, I give the directory where all my runs are in. The CPT plotpy will just look for any file in this folder which has a naming scheme with this ranks X threads pattern. So basically this, what you can see here, we give a prefix and then there's a dash and then it's ranks X threads. This is just the way that we defined it currently. So if you want this script to use, make sure your outputs are in this format, the names of the files, and it looks for this part. And since they are currently already running, I'm not going to run the script for now because I might get into trouble since some of the files might not have been written completely yet. But I also have the results. So once you run our script, you get this 4 outputs here, basically as a PDF or a PNG, but they contain the same thing. We have the graphs, which was the part that I showed you where we have this stacked up visualization of the parallel efficiency. The parallel efficiency goes down and the inefficiencies increase. and also the metrics, which is the total tables. And I have opened them here. So again, these are our results. We have first this little plot where we have the efficiencies, which is the output graph part. You can have it as a PDF or a PNG. It outputs both. And the second one is just the table. So we have our table. We have all the runs that I just submitted. And you can see how the parallel efficiency goes down due to the MPI load balance and the OpenMP load balance. Additionally, you get these computational scalability row here. And if I just add a sleep is an additional useful computation. It's not parallel runtime, it's just the sleep. So our total computation will go up. That's why the scalability goes down here. And you can apply this to your code easily. What we cannot do currently is fork off these, split up the computational scalability into our IPC scalability and frequency and instruction scalability. The reason for that is that we are currently not measuring hardware counters, but this is something we are currently working on. All right. Do you have any questions on how to use this tool? All right. I'm going to switch back to the presentation then, because I have a couple more things that I want to tell you. First, we have a thing called OTF-CPT options. It's an environment variable that you can use to control a couple of things. Mostly it is very straightforward. So basically we have a verbose option. If you activate that, you get a little bit more output. Though this output is a little bit more technical. So basically we give you the actual values of all the clocks we measure. So the outside OpenMP time, we give you the useful time per on the critical path, and also the MPI time, the outside MPI time. Enable is just if you want to have the same command without the OTF-CPT actually doing something, you can put that off. We have two path options that you can use to control where your OTF-CPT output should go, if it should go to the standard out or to some other path. And finally, we have this stopped flag, which controls if you want to start the measurement immediately or if you want to start in a stopped state. If you activate this flag, the OTF-CPT will wait for a P control or an OMP control tool call to actually start the measurement. And this is how you can limit the region where you actually want to use our tool. So in other tools, you have this region markers, and in our tool, we currently do not have region markers. What we do have is the P control that you can call once. Currently, you can also only call it once. So we have a single pair of start-stop markers that is possible. So you start in a stopped state, reach this P control call in your application. Then the OTF-CPT will start the measurement and actually get all these metrics. And then once you are finished with the region that you want to assess currently, we call P control 0, which stops the tool again. And basically in the end, you will only get the metrics for the region between the 1 and the 0 call from the P control. For OpenMP only codes, this is done with the OMP control tool. So if you have an OpenMP only code, of course, MPI P control will not be available as you don't use MPI. But basically, this does the same thing. We start the tool once and we stop the tool again. Okay.
I have two comments.
Yes.
One comment is
there are a couple of module files. You can use this module use command to get them. and they set your library path and the LD library path, so you can just use LD preload lib OTF-CPT.so. Also, they load the modules that were used to actually build this code. I've pre-built 3 combinations so far. If your code that you want to analyze and you want to use our tool on uses something different, please just tell me and I will try to get a module file out. Just tell me what you need and I will try it. Or you can just build it yourself, of course. Yeah, so do you have any questions on the OTF-CPT so far?